Greetings and welcome to my new calculus channel. My name is John Gabriel. So today I'm going to be discussing propositions 1 and 2 of book 5. Now remember, in the past few videos we've been going over the definitions in book 5, very important definitions. And so what I'll do is a little recap of the definitions and then I'll start on the propositions. So let's begin. Now, you'll recall that there are certain things we noticed about ratios. Well, first of all, the definition itself, which tells us that any given ratio, let's say Q to R, P to Q means P compared with Q, or that P has a relationship with Q, but we don't know if that relationship results in quotientness. Okay, in other words, do we have a common measure for P and Q? Okay, we don't know that right away unless we can find a common measure. And the common measure in this case is a magnitude, okay, not a number, because remember in book 5 we do not have numbers yet. Okay, those only come in book 7. And book 6 follows book 5, demonstrating the geometrical aspects of ratio and proportion. Then we also came across some rather interesting or not so interesting ratios. For example, the perturbed ratio, this ratio here. And we noticed that in some cases these may take, in addition to their relative positions, an extra position or a combination that will result in the proportion remaining the same, and that means such a proportion is perturbed. Okay, now proposition 1 states that, well, first of all, let's see what Heath says. Heath says that in modern notation m times a plus m times b is equal to this here. Now that's in algebra, but we haven't reached algebra yet, and so this proposition here isn't actually saying what Heath is claiming here, because already by this stage m is a measure, a is a measure, okay, and alpha and beta are measures. We don't have measures yet at this stage. Okay, so not only does Heath misunderstand the proposition, which does not say what he remarks, but he also forgets that in this particular book the notion of number has not yet been established. Okay, so there is no addition or multiplication defined as yet, as you see up here, addition or multiplication. And moreover, Heath incorrectly states that sums can be infinite by putting an ellipsis here. I mean, what else could he mean, right? Which is actually misleading and false, because the proposition doesn't state that, okay? And one cannot talk about many times in the context of infinity, which would mean that the proposition could not be proved if that were the case, because it could only be proved for a partial sum of a given series or a given sum, okay, and then transferring the property of the part over to the whole. So the only measure available at this stage is that of division. So the measure of each magnitude using one of its equal parts. So how does that work? Okay, so suppose we have two segments, the red segment, line segment, and the blue line segment, and these vertical bars are just there to denote that it's divided into equal parts. Okay, they're not really part of the line. And so the difference and the sum of line segments is at this stage only understood in terms of these segment lengths. Okay, so proposition 1 tells us that this line segment measures this line the same number of times that this line segment measures this one. Okay, that's all that it tells us. It's got the actual number of times is irrelevant, except to say that it is equal in either case. In this case, the number of divisions is the same, the number of measures. Okay, that's all. Now, Professor David Joyce of Clark University ignorantly states Book 5 is on the foundations of ratios and proportions, and in no way depends on any of the previous books. That's absolute garbage. It does, because It uses line segments, and line segments are derived as the first requirement of Euclid's 5 requirements, not axioms. But of course, mainstream academics, being the morons that they are, didn't ever understand that part of the elements, and in fact most of the elements itself. Okay, so book 5 very much depends on the previous books because it uses line segments to denote magnitudes and also the other primitive notions. So for example, measure, multiple, etc., all those are stated primitively in terms of magnitudes. So now, not only can one not talk about m times alpha plus m times beta is equal to m times alpha plus beta at this stage, but one has to wait until book 7 before all these properties are transferred through to algebra via the abstract unit. Okay, and that's proposition 1. Now, proposition 2, it's a slightly different case, which Heath thinks says this, but this is the algebraic identity, which at this stage doesn't mean anything to us. So let's see what the proposition actually says. It's stating that if 2 magnitudes are measured by the same magnitude, in other words, by A, if 2 magnitudes are measured, both of these magnitudes are measured by one common magnitude, right? One common magnitude, then the result is the same as the entire sum or combination measured by the same magnitude. So that means that if you had to put these 2 lines next to each other, in other words, combine or add them, then this would measure, this which is alpha would measure all of them, would measure the whole segment, okay? And then, of course, in algebra, this statement here means that alpha divides m plus n times alpha, okay? Read as A divides or measures m plus n times alpha, where alpha is denoted by this line segment or magnitude, because we're speaking about magnitudes in terms of line segments, okay, in terms of the lengths of line segments. But of course, even here, it's a little dangerous to say length, because length might give a connotation of number. So we don't actually deal with anything but the concept of magnitude. So that's proposition 1 and proposition 2 of the most important book in Euclid's Elements, which is book 5, which lays the foundations. And what I'm working up towards is the establishment of the arithmetic operations in proposition 12, the most powerful proposition out of all the propositions in Euclid's Elements. And that's where we get our arithmetic, the way we deal with fractions, the way we transfer all those properties through to algebra. And that's going to be very interesting. But in the meantime, I would strongly advise that you read this article, to which I'll place a link to in the details section, is how I discovered the concept of number. And by the way, I discovered this, it's not a long article, it's about 8 pages, I think, long before I even read Euclid's Elements, okay? And not surprisingly enough, it turned out to be what Euclid was saying, and stated even better than Euclid himself could state it. So, yes, I am 55% Greek, so maybe it's genetic memory. No, I'm not so sure there's even such a thing. But anyway, and this article is a very interesting article, which explains to you how you can derive the concept of number from nothing. So, hope you enjoyed this, and I look forward to speaking with you again soon, sometime in the future. I'm John Gabriel. This is a New Calculus channel. Till next time, goodbye.